So this will be the last lecture over mass spectrometry. So in this lecture, I just wanted to look at a few of the common pathways that organic molecules will fragment. And so fragmentation is mostly observed when you're doing electron impact mass spectrometry. So we'll just look at a few different functional groups and how they would typically undergo fragmentation. So alcohols. So alcohols would typically undergo what's called alpha cleavage. So between the alpha and beta bond. So electron impact mass spec. So first thing that would happen is you would knock an electron right off of the molecule to make a radical cation. And then that radical cation now, since you use such high energy electrons to knock the electron off, it has a lot of extra energy and it can dissipate that energy by fragmenting. So if we fragment the alpha beta bond, so we take this one electron and move it down to make a double bond and bring one of these electrons in the sigma bond over to make an oxygen carbon double bond, and then the other electron ends up on that carbon as a free radical. So you would make in this molecule the ethyl free radical, and so that has no charge, so that will not be accelerated to the detector, so you would not see a peak for that. But what you would see is a peak for for this. All right, so the starting alcohol had a molar mass of 60.057. So when you knock an electron off to make the molecular ion, well, that essentially has the same mass as the starting material because electrons don't have much mass compared to protons and neutrons. So that would be your parent ion peak at 60.057. And then if the ethyl group fragments off, well, if you add up the molar mass of ethyl, it's 29, or more specifically, if you're using exact masses of the different isotopes, then that would be the exact mass using the major isotope of carbon, carbon-12, and the major isotope of hydrogen, which would be hydrogen-1, then you get 29.039. So you would see then the peak at 31.081 for the fragment, and the mass difference would be the 29.039. Of course, how many decimal places you get the mass to depends on how an expensive of a mass spectrometer you have. So then you would typically see, then sometimes you may see this row like M-29 plus. So that would be the fragment peak. It weighs 29 less because of the ethyl group that fragmented off. So this, since this fragment is positively charged, then it would be accelerated by the electric fields in the mass spectrometer, and you would see a peak for that fragment, but not for the ethyl fragment, since the ethyl fragment is not charged. So that would be one way that alcohols fragment, is by cleaving the alpha beta bond. Our alcohols may also fragment by losing a small molecule, by losing water. So if you've knocked an electron off of oxygen, and then it can fragment. So basically that oxygen picks up a hydrogen to form your water molecule, and then oxygen leaves and takes those two electrons with it. So now oxygen is neutral, or water is neutral, and then you have this as your radical cation. So in that case, you would see a mass for the radical cation, but it would be a mass 18 mass units less, so 42. So then if you see a peak here at 42, where the mass difference is 18, then that would mean a water molecule fragmented off. So atoms with lone pairs will typically fragment as alcohols do by cleavage of the alpha beta bond. So just another example, so this is an ether. So if you knock an electron in the ionization chamber off of the oxygen, and now you have a radical cation, and that undergoes cleavage. So move that electron over, one of those electrons over to make the oxygen carbon double bond, and that electron stays there. So again, in this particular molecule, just because of the carbon structure, you end up with an ethyl radical, and then that's the fragment peak that you would see in your mass spec. So amines are similar, since nitrogen's got a lone pair, so you can knock an electron off of nitrogen to make the radical cation, and then if that undergoes alpha beta bond cleavage, so again, move one of these electrons over, move that down to make your double bond, and the other electron in that bond stays behind on methyl. So you get the methyl radical, which has a mass of 15. So that would be, and then this would be the cation that you see, and because that would be accelerated by in the spectrometer, so that would be hit the detector, it would just have a mass 15 units less. So in general, for amines, alcohols, ethers, you would cleave that bond, so you would lose a mass of whatever the mass of R is, would be your delta mass, change in mass for the what would end up being the fragment peak. Okay, so for ketones, so again, anytime with an atom with a lone pair, you're going to knock an electron off from the non-bonded electrons, and then this ketone can fragment by cleaving the alpha bond. So that's going to be by cleaving right that bond. So what we want to do is move one of these electrons from that bond over to make a double bond between, a triple bond now between oxygen and carbon, and this other electron would go to that carbon. So in this case, you would get a primary radical, and that would be the fragment peak that you see in the mass spec. So of course, it could have cleaved the other alpha bond. So you could have took one of these electrons, and then you would have got a methyl radical out. But in either case, you get that, well, no, that would be a different mass, right? Those two fragments would have different mass. So either of those cleavages could work, and you would probably see a peak for both fragments. So you'd see a peak for both fragments in the mass spec, but one is preferential over the others. So which one would be preferential? Well, primary radicals are more stable than methyl radicals, so this would be the preferred pathway. So ketones, aldehydes, anything with a carbon-oxygen double bond basically can undergo what's called a McLafferty rearrangement, where you cleave the alpha-beta bond. So what happens in this type of fragmentation, so again, we lose an electron, or let's see, so based on the drawing that I did, so I have it shown using that electron. Of course, it doesn't matter which one. So we lose an electron from the oxygen, and then if we count 1, 2, 3, 4 carbons away from oxygen, and if we sketch these hydrogens out, then what can happen is oxygen takes a hydrogen atom, and then the other electron in the CH bond, we move down to make a double bond there, and we move one of these electrons over to make a double bond there, so you get this alkene fragmenting out, which you don't see the mass for that in the mass spec, but you do see the mass difference. And then we take the other electron and move it onto that carbon. So then this would be your radical cation, which you would see a peak for in your fragment as a fragment. So why does it fragment like that? Because this cation is relatively stable. Right? How is it stable? Well, you can draw a resonance structure for it. So we'll move that down to make a double bond, move one of these electrons over and the other electron on the oxygen, and then you can draw this resonance structure. So in general, the way molecules fragment is to give something that is relatively stable, and in this case it's stabilized through resonance structure. So alkenes will fragment to give an allylic. They'll fragment at an allylic bond to give an allylic carbocation. And so that allylic carbocation is resonance stabilized. So again, so that's the common theme, is that fragmentation usually occurs to give something that's more stable if possible. Okay, so for the alkene, so that's the alpha carbon, so that's the allylic carbon. And so then it's going to cleave the alpha beta bond. So you knock an electron off of the molecule, make the radical cation, and then the R group breaks off, and you end up with this allylic carbocation. And so that would be the peak that you see, whatever the mass that is in the mass spec. And so this is stable, right, because it's resonance stabilized. Okay, so if this was your molecule, so 1, 2, 3, 4, 5, 6, so if you took the mass spec of that, so again, you knock an electron off of the molecule somewhere, and then when it fragments, right, it's going to fragment there. Oops. So you lost an ethyl group, and then that would be the fragment peak that you would see. So ethyl group again has a mass of 29, so this molecule has a mass of 84. So if you took and then this molecule, or this allylic cation has a mass of 55, so if you took the 84 minus 55, you get 29. So you would know an ethyl group broke off of the molecule. So there are tables there are databases that have tables of fragments. So if you can calculate the mass difference, and then you can look in these databases, you can figure out what broke off of your molecule, and that's how you can get structural information about your molecule. So aromatic compounds would be the same concept. They would typically fragment again at the alpha beta bond. So you knock an electron off of the molecule, and then it fragments there, so that you get a benzylic. Benzylic cation. And so that would typically be then the largest peak, the base peak. If you remember, the largest peak is called the base peak. That's arbitrarily set to 100% intensity. That would typically be the largest peak if you have an aromatic compound, because the benzylic cation is very stable, right? You can draw resonance structures of it. Or you delocalize that positive charge into the benzene ring. Right, 3 significant resonance structures, so it's a very stable carbocation. So that's where the aromatic compounds are going to tend to fragment off, so that will typically always be the largest peak. The base peak is by fragmenting at the alpha beta bond in an aromatic molecule. Okay, so fragmentations can be very complex, as this next example shows with an ester. So if you knock an electron off of oxygen to make this radical cation, then similar to a McLafferty rearrangement, it can abstract a hydrogen atom, right, four atoms away from the oxygen. And then I've just simply redrawn this molecule, so that now that's your radical cation. So that's a rearrangement. You basically just moved a hydrogen atom from carbon to oxygen. And if we redraw this so that we sketch out the hydrogens on this carbon, then this can undergo another rearrangement. So we're going to take one electron from here and one electron from that bond to make an oxygen hydrogen bond, and the other electron here and that there to make a double bond there. And then this other electron goes here. So now you make that allylic radical that fragments off. So that would be your mass difference, and then this would be the fragment that you see in your mass spec. So this one has a mass of 61. So rearrangements or fragmentations can be very complex in mass spec. Okay, so just to summarize some of these fragmentations. So if you have alkyl halides, alcohols, ethers, amines, and that it's a pretty significant chunk of organic molecules, then 3 common pathways that they can fragment, right? So you knock an electron off, and then they can undergo cleavage of the carbon-oxygen or carbon-chlorine, bromine, fluorine, iodine bond, right, to give that carbocation. Or they can undergo the alpha cleavage, right, where we move that electron over, that electron down to make a double bond, and then fragment off that free radical. Or they can undergo the small molecule fragmentation, so losing a water molecule, for example. Where this picks up, let's see, let's get my electrons right, that goes there. So take that electron, make a bond from oxygen, if it's oxygen, or it could be chlorine to hydrogen, and this takes its electrons with it, and that electron stays behind on carbon. So then you have that radical cation and a water molecule, for example, or an HCl or HI or HBr molecule. And so you may see this sometimes represented like that. The double bond cation would just mean that pi system is missing 1 electron. Okay, so that are some of the fragmentation pathways that you see for organic molecules. We're not going to cover these in any more detail. I just wanted to show you some of the basic fragmentation patterns. But you know, fragmentation patterns can be very difficult to interpret in mass spec. So we'll just look at some basic examples, and you'll just have to know some basic examples of how that works.